Hey everyone, my name is Gustav Söderström. I'm co-president at Spotify. I was asked by my colleagues to do a deep dive on AI for all of you, from engineers to executives at Spotify, specifically on this new type of generative AI, and try to explain how these things actually work. How is it that we have services like Chat GPT, where you can create an entire novel, or services like Stable Diffusion or Midjourney that can create beautiful images and even music out of just text or white noise? Now, for us as employees and executives in the tech industry, it is quite literally our job to understand this. But I think that even if you're not in the tech industry, it is almost an obligation to understand what is going on right now, because this is a big thing. People will talk about 2023 100 years from now, because this is the year that computers started passing the Turing test, meaning that they could pass for being humans to someone who doesn't know if they're speaking to a computer system or to a human. And I think people will talk about this 100 years from now, just as I'm talking to my kids about splitting the atom almost 100 years ago. And I feel that if I were there, in the 1930s when we split the atom, I would have liked to understand what was going on. I wouldn't have liked to have realized 20 years later that it happened and I was there, but I was actually unaware. So I think it's important for everyone to sort of at least get intuitions for what it is that has happened and how it works. So my bold upfront promise to you is that after this presentation, you will feel like you do understand what is going on, even if you don't know a lot of math. Unfortunately, I found that it's pretty hard to actually get a grip on what is going on, and I think it's partially because of this. So George Bernard Shaw created this notion of conspiracies against the laity. And what it means is really, so laity, for example, could be the priest class. And what it means really is that any profession tends to raise barriers towards other people entering that profession. This could be deliberately by creating certification authorities and rule system around this profession, but also less deliberately, but just creating very complicated vocabulary and lingo around this profession. You all know what I mean. You take something like finance or legal, and you often get this feeling that it seems very complicated and hard to understand. And then when you actually do understand it, you kind of ask yourself, like, why couldn't they just have said that? Often the vocabulary itself makes it seem harder than it actually is. Now, it's often not actually deliberate. It is a fact that specialized groups tend to create specialized vocabularies because it's more effective for them to talk to each other at sort of a higher level, but that also creates these barriers to understand what is going on for everyone else. I think the problem that makes it seem more complicated than it is that people confuse theory with practice. And while the practice of getting these things to really work is very complicated and actually does require a lot of math, the theory actually isn't. I think it's entirely possible to build intuitions about what is going on without having to understand the practical problems. So let's try to see if we can expose this conspiracy. Now, for those of you who know this stuff well, you will see that I take a bunch of shortcuts here and there, and that the actual numbers and percentages don't always make full sense. But you'll have to indulge me, as I'm trying to keep it simple and just keep it true enough to create largely correct intuitions. Are you ready? Let's go. So what is an LLM? Well, LLM stands for Large Language Model. And this is the thing that powers something like Chat GPT. So after this section, hopefully you'll understand how Chat GPT actually works. But there are a bunch of steps we have to go through. The first step is to understand how you even get a computer that literally only understands numbers to actually understand language. Well, there is a pretty straightforward intuition to understand roughly what's going on. So let's say that you as a human, you take the English dictionary, you just start at the first word. So ace, then amazing, then appreciative, aromatic, all the way to the last word. And there's about 600,000 words in the English dictionary. And you just give them a number. So the first word, ace, has number 1. Second word, amazing, has the number 2. Third word, appreciative, has the number 3, and so forth. So now you can literally take a sentence in English, let's say, hey, how are you? And you can just look up every word and see what number it has. So for a computer, a sentence like, hey, how are you, is not actually a sentence, it's just a sequence of numbers. So the word hey has, for example, the number 25, the word how has the number 30, the word are has the number 5, and the word you has, for example, the number 75. Now, you may see that these are very small numbers, but that's just to keep it simple. So it's just a lookup table. You have this long list of 600,000 words, a unique number for every word, and you just translate a sentence into a sequence of numbers. So let's go into a bit more detail. How does this actually work? Well, let's start with this super simple model. Let's say that we have this Excel sheet where we have every word in the English dictionary as a row, and then we have every word in the English dictionary as a column. So for every word, we have a percentage for how likely every next word is. So let's say we get the word are. To a computer, that means you get the number 5. And now the job of the language model is to say, what is the most likely next word after the word are? Or more correctly, what is the most likely next number after the number 5, which represents the word are, according to all the words or all the sequences of numbers I've seen on the internet. So you could imagine that as a human, you might give an equal percentage to a lot of words. It could be are you, because maybe the sentence is literally, hey, how are you? But it could be are they? It could be are things, because the sentence may be how are things? It could be are fine, because the sentence may be they are fine. Because you only have one word to guess from, one word of context, it's going to be hard to guess correctly. You literally can't guess correctly. You don't have enough information. But you can do a good guess. So maybe these things like you, they, things, fine, they have the same percentages. But you're going to have words that have a very low chance of being right. Are animals is a very uncommon sentence on the internet, most likely. It happens, it's just uncommon. So again, to a computer, it's not guessing words. What the computer would say is, based on all the text I've seen on the internet, or more correctly, based on all the sequences of numbers that I've seen on the internet, according to this translation from words to numbers, after the number 5, I usually see the number 75, which represents you. Or after the number 5, I usually see the number 42, which represents they. Or after the word 5, I've usually seen the number 97, which represents things. So it's doing something very similar to what you would do as a human. And as a human, you have intuitions about the percentages, and I think it's easy to understand that if a computer could just look at all the statistics over all of Wikipedia and all the internet, it could also have a pretty good idea about the percentages and the statistics about the next word. All right, so this is as far as we get with this one column of 600,000 rows, or 600,000 rows and 600,000 columns. Now, let's say that we get one more word of context. So instead of are, we get how are, which to the computer, again, is the numbers 30 and 5. Well, now the percentages change. For you as a human, when you just had the word are, there were, you, things, they, fine, were equally likely. But when you get two words, how are, all of a sudden, you is probably more likely. Maybe it's 50% likely now. Because it's more common to say, how are you on the internet than how are they, for example. So if you had to guess, you'd probably go with how are you. And it's even more likely to say, how are you or how are they than how are things, perhaps. And if you take something like fine, which was pretty likely when you just had one word, because are fine could happen if you say they are fine, no one says how are fine. So now all of a sudden, the word fine has a very low percentage. Translating this to numbers, what it means is the large language models now has two numbers to guess from, and just like you as a human would guess much better with two words, the large language model, based on all the numbers it's seen on the internet, is going to guess much better with two numbers as well. You can imagine what comes next. What if you had three numbers or three words? So now the context is, hey, how are, or the numbers 25, 35. Now your guess is going to start to get really good. Hey, how are you is now very likely. Let's say it's 70%. Hey, how are they? Maybe even less likely. You might say, how are they? But you seldom say, hey, how are they? Because they are not in front of you. So that might go down to 5%. And something like hey, how are things, that was a bit less likely than how are they, now shoots up, because hey, how are things is something you would see on the internet quite often. And then hey, how are fine, and hey, how are animals, very low percentage. So the whole point is, the more context you get as a human, the more words you have, the better your guess, the more sure you're going to be about the next word. And it's the exact same thing for a large language model. The more numbers it gets, the numbers represent word, the better its guess is going to be on the next number. So in a sense, this is all that a large language model does. It just guesses the next word, or more correctly, the next number from previous numbers. And so it's actually a little bit of a misnotion that we call them large language models. They should probably be called large number models or large sequence models, which they are called sometimes. Because it turns out that you can turn words into numbers, but everything are numbers. You can turn pixels into numbers, or actually pixels are numbers. So you can put pixels or an image into these large language models, and based on the previous pixels, the previous pixel numbers, the RGB values, it is going to get very good at guessing the next pixel. You can put audio samples, for example, from someone speaking. Those are just numbers. And if you have those numbers and you train on those numbers, a large language model will get very good at guessing the next sample in an audio sequence. So remember, it's not a language model. It's actually just a number model. And everything in the world can be translated into numbers. So anything that is a sequence, if you have lots of data, these models can learn the statistics about those sequences and correctly guess the next number. So in a sense, now you actually understand what a large language model does, but there is a problem here that you should understand. Why hasn't this happened before if it's so simple? Well, even though it's simple in theory, it's quote unquote just statistics, just guessing the next number. It turns out that guessing the next numbers for long combinations of context for many words is very computationally intensive. So if we go back to your Excel sheet, where for every word, you have a percentage on how likely every other word in the dictionary is. Now, I said there were about 600,000 words in the English dictionary, but let's just simplify it and just take like the most popular 50,000, because 50,000 is like roughly the size of a vocabulary that a large language model actually uses. So now we made it smaller. You now have 50,000 rows of words, and you have 50,000 columns for every such word. So that's 50,000 times 50,000. So that's actually a pretty big Excel sheet. It's like 2.5 billion cells or something. So pretty unwieldy Excel sheet, but it's still like sort of doable. It's a lot of cells, but it's doable. But this is just with one word. And remember, when you just had one word to guess from, your guess is going to be pretty bad. Now let's say that you get 2 words to guess from. So now you're going to have 50,000 rows times 50,000 columns, and then times 50,000 again, because you have combinations of 2 words. So now you have something like 125 trillion cells in your spreadsheet, and it's getting beyond what is solvable. So it turns out, while the theory, as I said, is deceptively simple, the practice is actually very hard. It's just very, very hard to do these statistics in practice. Enter the transformer. So there's this paper that came out from machine learning scientists at Google in 2017 called Attention is All You Need. And it suggested a specific machine learning architecture called the transformer, which is what you see on this image. And don't worry, you don't have to understand this image at all. It's just going to look cool if you say like, oh, I recognize that, it's a transformer. The only thing you really need to understand is that they managed to find a clever way of solving this problem of how do you have a lot of context. Turns out a transformer can handle thousands of words. In fact, it can handle tens of thousands, and recently even something like 100,000 words as context, just to guess the next word. So think about that. Like 100,000 words. That literally means that the job that you would have as a human is you get to read an entire book, and you just hide the last word on the last page. But you have the entire book as context to guess the missing word. I mean, your guess would be amazing, right? You would be almost completely correct in that guess because you would have so much context. Even if that missing word was something very unlikely, let's say that the story ends, and then she went to, right? And maybe the correct word is Pluto, but you would know that because you know that the rest of the novel was about space and she was on her way there, right? So you would be able to make even very unlikely but correct guesses because you have context. This is the problem that the transformer machine learning model solves, so this architecture. And the reason the paper is called Attention is All You Need is because the way it solves this is that it allows the model to literally pay attention mathematically to put different weights on different words. It doesn't put the same weight on all the words, so the problem doesn't blow up in the same way as your Excel sheet did. It can pay attention to different words depending on the guess. Now, if you want to know more about this, you can read about it, but the only thing you really need to understand is that the transformer model solves the context problem in a very clever way. And if you want to go into this, don't be afraid. The math isn't that hard. It's actually mostly a bit of linear algebra, a little bit of calculus, but not the hard stuff. This is not quantum mechanics. So if you want to go there, go there. But this is what everyone is talking about. This is what the transformer model is. It simply allowed machines to do these statistics on internet scale. All right, so now we come pretty far. So now we have this thing that is very good at guessing the missing word. So let's take this sentence, for example. My dog's name is Ben. He's a big dog with large paws. Ben likes to play fetch with me. Let's say that the large language model tries to hide the word fetch, right? So it is on the word play, and it's supposed to guess the next word. Well, you can imagine in the model, where you just get the word play, the best guess would maybe be play soccer. It's the most common word on the internet. Play basketball, maybe. Play fetch is pretty uncommon. But now that you have context, the language model can say that who is playing? Well, it's Ben. And then it goes even further back and says, my dog's name is Ben. He's a big dog. So now it knows that Ben is a dog. And now all of a sudden, with that context, the most likely next guess probably is fetch, because that's the most common word or number to follow that sequence of numbers. So now we have this attention-based transformer that is very good at guessing the missing word, and it can train itself on the entire corpus of text on the internet. So we're almost there. So now we can generate language. How do you generate language? Well, let's say that we have this sentence, how are the numbers 30 and 5. Now, all you do when this model is trained is you say, what is the most likely next word according to everything you've seen on the internet? Well, it's probably going to say the most likely next word after how are, or the most likely next number after 30 and 5 is you, okay? So then you add the word you. And then you take the text you just generated, and you put it back into the model and say, now given this text, how are you? What is the most likely next word? And then the model says, okay, after how are you, I think the most likely next word is I. Okay, so we add that. And then we take the sentence and feed it back into itself again and say, after the sentence, how are you, I, what is the most likely next word? It's probably going to say something like, the most likely next word is am. And then we add that. And now we feed this into itself and ask, what is the most likely next word? It's probably fine. And this is how you build sentences, and you can just keep going forever. So what you do with these language models is you put in some text, some numbers, and then you just ask it to fill out the likely next number, take that, feed it in again, add the most likely next number, take that, feed it in again, forever. This is what is called an autoregressive model, by the way, if you ever hear that word. It just takes the context and tries to guess the most likely or one of the most likely next words. So now we can do something like this. You could, for example, feed in half of a Shakespeare text into the large language model, which to the language model, again, will be a long series of numbers, but it will have seen these numbers on the internet. There's a lot of Shakespeare text on the internet, Shakespeare or Shakespearean text. So it's going to say like, hey, I recognize these numbers. I know what comes next. So if you just take the most likely next numbers again and again, you are going to get something that is either very close or quite literally actually the rest of this Shakespeare play. So that's pretty useful. Now we have this thing that can take a piece of text and complete it with something very likely, often actually, if it existed on the internet, not just very likely, but even the exact same thing. Because if you see a lot of the same Shakespeare play, those exact words of the Shakespeare play are the most likely next numbers, right? Okay. But what about creativity? We just said that Chat GPT doesn't just repeat the things you've seen on the internet. We just said that it can write poems that never existed. It can write new text. So how does that work? Well, we need to go one level deeper to understand this, but bear with me, because we're almost there. Now you need to understand something called temperature. So what we said previously was that we have the words how are, or to the computer the numbers 30 and 5. And we said that we took the most likely next word, which is you. That's if the temperature is 0. Let's imagine that 0 means you take the most likely next word. And then you take the most likely next word after that, which is I, most likely next word after that, which is am, most likely next word after that, which is fine. And so you're going to get this sentence, and you're actually going to get this sentence every time, because these words will always be the most likely. So there's this misunderstanding that large language models are probabilistic, meaning that they give different answers every time, because when you use ChatGPT, you actually do get different answers every time, even for the same query. But in reality, large language models are very much deterministic. If the temperature is 0, if you take the most likely next word, of course, the statistics don't change. You will always get the exact same sentence. What is happening in these large language models is that when you want them to be a little bit creative and not just boring, not just repeat what you already know from the internet, you actually do something different. What you can do is you can pick something that is very likely, but not the most likely. So think of it as, instead of taking the word that is the 100% most likely, which in this case would be you, and it will be you every time, you randomize a little, but around the most likely words. So you're going to pick one of the likely words, but not necessarily the most likely. So you're still going to take a word that is very likely. And that's important, because if you take a word that is very likely, the sentence is still going to make sense grammatically, because the word is likely, and it's still going to make sense semantically, because the word, or number in the case of the machine learning model, is likely. So let's say that we take not the most likely word you, but we take the second most likely, which is they. So now you actually created text that never existed on the internet. The statistics are likely, the sentence is going to make sense, because you're picking something that statistically comes after how are, but it's not a copy of what existed on the internet. It is, by definition, something new. And this is called raising the temperature. The more you raise the temperature, the more you sort of randomize around the most likely words. And you can imagine that if you stay very close to the top, it's going to still be quite similar. It's going to be new. It will not have existed on the internet, unless by chance, but it's not a copy of what existed on the internet. It will be novel, but it's going to be very close to what exists on the internet. And you can imagine that the more you raise the temperature, the more you randomize, the further you go from the most likely, the more creative the model is going to get. But if you go too far, it's going to start to pick words that are unlikely. So if you raise the temperature too much, it might just say, how are animals? And so quite literally, if you raise the temperature too much, the model goes from seeming very creative to starting to seem a bit unhinged and insane. And I think it's a very interesting analogy to humans here. It tends to be the fact that the most creative humans are somewhere on the borderline of very creative, and sometimes they just seem crazy. And maybe that's a coincidence, maybe it's not. Maybe they just have a higher temperature than the rest of us. We'll know someday. All right. So now we have a large language model that can not only complete a piece of text with the most likely text, but if you raise the temperature a little bit, it can actually complete the text with something novel that never existed before. So now we're pretty close. This is actually GPT-3, which was about a year and a half ago that came out. That was sort of an autocomplete on steroids. It could take some text and it could complete it very believably. And if you raise the temperature, it could complete it with something that was never written before, right? But it wasn't Chat GPT. For those of you who had access to it, it was quote unquote just an autocomplete on steroids. So a way to think about where we are now and where OpenAI and other companies were about a year and a half ago, this GPT-3 stage, it's called a base model. And you can sort of think about it as maybe a kid or sort of an unhinged teenager. It has a lot of knowledge about the world. It can complete text. It can generate text that never existed, but you can't really steer it. You can't really format it. So what you would like to have is something like Chat GPT, where it doesn't just complete sentences, it actually answers your questions. And you would also like to be able to steer it to stay away from certain areas and talk about other areas. Maybe you would like it to not answer questions about how to create a bomb, for example. So how do we get to that last stage? Well, that requires two things. Something called supervised fine-tuning, SFT, and something called reinforcement learning with human feedback. Again, conspiracies against the laity. SFT and RLHF, that's exactly how you get people to stay away from your profession. So let me dig in to what it actually means. Again, it's not very complicated. So let's start with supervised fine-tuning. Now, we said that what we have now is this machine that can take a sequence of numbers and guess the best next numbers. So it's your iPhone autocomplete on steroids. Now you could imagine that if you take a bunch of documents from the internet that happen to be Q&A documents, right? So there's a question and someone else answered it. If you train the model on autocompleting that, it will learn the pattern that every time I saw a question, those types of numbers, questiony type of numbers, there was always an answer. So if you're lucky, even with the base model, if you pose a question to it, and it has seen a lot of question answering dialogues on the internet, it may actually give you an answer just because it's a pretty common numerical or language pattern on the internet. So you could say, Q, what is the width of the earth? And it could say answer some number, right? But it could also just answer with another question, because that's also common on the internet, on all the documents it's seen, that you have question, 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 question. For example, like a math test and no answers. So it's kind of like, it has some of this knowledge about question and answering, but it's not deterministic. Sometimes you get what you want if you sort of ask it to autocomplete the right structure, sometimes you don't. So what you do with the supervised fine-tuning is, whereas the base model was self-supervised, like it literally trains on all the text on the internet by hiding one word from itself at a time, or one token. And by the way, for those of you who know this, one token is not exactly one word, but for purposes of this presentation, let's say one token is one word, is one number. So the base model trains itself on all of the internet. So trillions of tokens, of text. Now you do something different. You create a small supervised data set. What does supervised mean? Well, it means that unlike the self-supervised, this is supervised by humans. So now you create a bunch of documents that are just the format you want. It's always a question, always followed by an answer. And you create, let's say, pretty small number compared to the internet. Let's say 10,000 of these documents. So now you ask humans to go and create 10,000 documents of questions, answers, questions, answers. And then you take this base model, which train on the entire internet, and you do what is called fine-tuning. You train it a little bit more. You don't start over. It's already trained. You just train it a little bit more only on this data set. That is always a question and answer. And then what happens as an intuition is, you can almost say that the language model keeps all its base knowledge, but then it learns this behavior. So it's going to start answering everything as an answer to a question, just based on this little extra data set at the end. You can almost think of it as, it sort of remembers what you did at the end. And if you overrepresented everything should be an answer to a question, it's going to start mimicking that behavior. So now it takes all the world knowledge it has, but it always answers it as an answer to a question. So now we're really close. Now we went from iPhone autocomplete on steroids to a question answering machine, where everything you put in will be formatted and answered as if it was an answer to a question. So now we have an assistant, but this assistant still doesn't have any real behavior or values. It's just going to reflect whatever values and behaviors and statistics are on the internet. Some good, some not good at all. So there is one more missing step, which is when you ask that question of, how do I create a cheap bomb out of chemicals from my store? how do you get this thing to not actually answer that question? We just trained it to always answer a question. This is where reinforcement learning with human feedback comes in. So this is yet another step where you use humans. So now we have this language model that you can ask questions and it gives answers. And sometimes it gives answers we like, sometimes it doesn't, both in the content, but also maybe in the formatting. Maybe it answers a question with too much text or too little text. So what we do now is a really clever step, which is we take a bunch of humans again, and we're talking about not millions, but a few thousand. And we take a single question and we ask the language model this question. And then we get a bunch of different answers. Remember, the temperature is not zero, so we don't get the same answer. We raise the temperature a little, and so we're going to get a lot of different answers for the same question. So one question, a bunch of answers. And then you ask these humans to rank the answers. So for this same question, which of these, let's say 100 answers, did you like the most and the least? And you rank them. You give them a score. Let's make it simple. Let's say it's 10 answers, and you as a human are supposed to score them from 10 points, 9, 8, 7, all the way to 1. Best to worst. So now you get a new type of data set where for the same question, you know what a good answer looks like according to a human, and you know what a bad answer looks like according to a human, and in between. So this is a new type of data set. And now what you do is you take another machine learning model, or actually technically also a language model, and you train it on a little bit of a different task. So what you do is you take the question that you had, and you take one of the answers that you had, you put them in together, and you ask the machine learning model to guess how would a human have scored it. Was this the 10 answer to the question, or was this the 1 answer or the 5-point answer? And then you train it until it gets really good at predicting that this type of answer, a human would have scored 10. This type of answer, the human would have scored 1. So now you build something called a reward model, a model that is good at guessing, based on supervised data from humans, what the human would have thought about this answer. Okay, so now we're almost there. So we have the large language model. We super fine-tune it to always answer as if it was asked the question. And now it produces answers, but it produces answers of varying quality. Now we have this other model, which is a reward model, that can look at an answer and say what a human would have thought about it, if it was good or bad. Now you just take these two models, you hook them together, and you just let it go. This is the reinforcement learning part. Now it can supervise itself again. It takes a question, generates an answer, scores its own answer and said, that was bad, I should do better, I should do this. It scores that answer and said, that was good according to human, I should do more of this. So now it can train itself against the reward model. This is what is called the reinforcement learning. And this is a closed system where you don't need humans, so you can do this millions, tens of millions, hundreds of millions of times until it gets really good at answering, not just in the format that a human wants, but also in the style and literally if you choose the values that a human wants. So I think this is interesting because people ask, like, what does this model think? What are the values? And the truth is, in the base layer, the values of the model are just an average of the entire internet. It is what the internet thinks, good and bad. But the reinforcement learning step is actually what inserts a certain behavior. And that is actually a pretty small group of humans. So that is where a lot of the responsibility lies for how this model behaves. All right. That is Chat GPT. Now you understand how it works. You've gone from back in history all the way to 2023. You understand how these things are passing the Turing test. It wasn't that complicated, was it? At least you can imagine how you as a human would solve these things if you had infinite time and infinite big Excel sheets. So now one question is, why is everyone so surprised? And why did, quote unquote, no one see it coming? Some people claim they did, but most didn't. Even machine learning scientists are very surprised in general about how quickly this happened. And the machine learning models themselves aren't that new. The transformer architecture in 2017 was clearly an innovation, but language models has been around and modeling language has been around for a long time. So what was it? What was it that surprised people here, including the experts? Well, it was the scale and speed. So the notion of guessing the next word was not something that was recently invented. People have been trying to do this for a long time. And when the transformer architecture came along, it became easier to do it at scale. But what wasn't obvious was that just doing this simple thing much more would start giving completely new behaviors, what is called emergent behaviors. So you could see these large language models not being very good at certain things, like math, for example. And then without changing the architecture, just by scaling it up, all of a sudden it started getting good at things. And that was surprising, that you would sort of get these emergent capabilities that many people thought would require some new mathematical or architectural innovation. So just that scale alone improved performance was very surprising. The other thing that I think is surprising to most non-machine learning people is this creativity thing. Now, the temperature notion was not surprising to people in machine learning. It's been around forever. But again, the concept was there, but even machine learning people were surprised at that it actually scales to something that looks very much like human creativity. It is very, very much unknown if this is what we do, but certainly the result looks like what we do. So either we got the type of creativity that we have, or we managed to simulate the type of creativity that we have. And that surprised people. And lastly, the thing that was missing was this ability to steer it. The supervised fine-tuning to give it a certain behavior, to be an assistant, and then the reinforcement learning to be able to use it practically. You know, GPT-3 was really cool as an autocomplete, but it was a bit unhinged. And supervised fine-tuning made it the interface workable because it was Q&A machine, but it was still unhinged. And reinforcement learning with human feedback made it practically useful in reality. So those were the unlocks. And I think what is really interesting here isn't that we're not surprised that we finally sort of managed to crack intelligence and how complicated it was. What surprises people is actually the opposite, that we kind of cracked intelligence and it was so simple. It's almost provocatively simple. And I think what this does, so about a year ago, around Chat GPT or GPT-3, these models were often called, quote unquote, just statistical parrots. And that was meant as a derogatory term. Or actually around GPT-2, they were saying like, these are just statistical parrots, meaning that they just parrot back, as I said, statistics from the internet. Like, this isn't real intelligence. It's not very impressive, actually. Maybe useful, but not impressive. But then, as GPT-3 came along, GPT 3.5, Chat GPT, GPT-4, this question of, aren't these things just statistical parrots, turned to, oh crap, what if we are just statistical parrots? And so it really puts a mirror to ourselves. And it gets a lot of people to start thinking about what they are, which I think is very exciting. All right, so we did the first part. We actually went through what a large language model is and how ChatGPT works. And now I think you have as good intuition as most people about what it is that actually happened. So now, hopefully you have at least an intuition for how something like ChatGPT works, why it works the way it does, how it can understand questions and answers, and why when you ask it how to create a bomb, it doesn't actually tell you, and rather it says, as a large language model, I'm not going to answer that question. This is the reinforcement learning with human feedback part. All right, so you understand that language is sort of just statistics because language can be represented as numbers, and maybe they are even to us actually, and numbers are just statistics. But I want to teach you one more thing that I think is really cool. Again, made overly complicated. It's not actually that hard to understand, but once you understand it, your mind is a little bit blown. So you may have heard about something called vectors or vector space or embeddings or codes or distributed representations, all of these fancy words without necessarily fully understanding what they are. I'm going to explain to you what they are. I'm going again to show you that it's a very straightforward concept, but still very, very cool. So we said that language can be represented as numbers, and you can simply give every word in the dictionary its own number. But it turns out that instead of giving a word just one number, which you can do, you can also do a little bit better than that. So you can take a word and you can represent it, instead of just saying the word R is the number 54, you can say I'm going to use like 3 numbers or 4 numbers to represent the word R. What do I mean with that? Well, let me show you. Let's take a very simple world. Let's say we live in a universe that only has 3 dimensions in it. Only 3 dimensions. Things are either royaltiness, they are masculinity, or they are femininity. It's a very simplified universe. It only has 3 dimensions to everything. So now in this universe, you can take a word, for example, like king, and you can say, instead of just saying king is the number 29, you can say how much of these dimensions are in the word king. So you can say that the word king has almost 100% royaltiness, so 0.99. Nothing in statistics is 100%. So 1 means 100%, 0 means 0%. So 99 means almost 100% royaltiness, right? Because the king is almost always a royal. But the word king is also very high on masculinity. It's almost 100%. We don't know. Most kings so far have been men historically, we think. And then you have femininity, which is low. Probably not 0. Nothing is ever 0, but low statistically on average. So 0.05. So now, instead of a single number for the word king, you have 3 numbers, which corresponds to some dimensions of how much of something that word is. Now, let's take another word. Let's take queen. So queen is also about 100% royalty, right? A queen is almost always royal. It is very low in masculinity, so let's say 0.05, almost 0, and very high on femininity, 0.98, for example. Let's take another word, woman. So a woman could be royalty, but statistically across the population, pretty low. It's almost 0%. Very low in masculinity and very high on femininity. Let's take a word like princess. So princess is interesting because it is almost always royalty. It's very high on royalty. It is usually not masculine and very high on femininity. All right, so now we have these 4 words described not as single numbers, but as numbers that represent how much they are of some dimension. And in this simple universe, only 3 dimensions: royaltiness, masculinity, and femininity. So now we have these words not described as a single number, but as several numbers. And these numbers actually represent how much of something, of some dimension, are in these words. In this simple universe, we just have these 3 dimensions, how much something is royalty, masculinity, and femininity. But you could easily imagine, as we did before, that instead of just these 3 dimensions, you literally take the entire English dictionary as dimensions. So maybe you could have a dimension that is age, and you could say the word king, if 100% is old age and 0 is young age, a king is maybe 0.7, 70% in terms of age, usually old. Queen, maybe 0.6, a bit younger on average. A woman, literally 0.5, 50%, right in between, whereas a princess would be usually young, so maybe 0.1. And you could just go down the English dictionary, and as a human, you can intuit that you could try to put a percentage on how much of every word in the English dictionary is in every other word of the English dictionary. Does that make sense? So you take the word king, and you take, in the worst case, these 600,000 words, and you try to put a percentage on how much is king royalty, masculinity, femininity, age, car, things that would be 0%. So most of these would actually be 0%. But you can imagine a very long vector. We have a percentage for how much of every word is in every other word. So it would be a vector that is 600,000 numbers. And in reality, that's not how you do it. These models usually have about 1,000 dimensions, and they sort of pick the most useful dimensions. And I'll come back to how it picks them later. But it could be good to know if you're wondering, like, seems unwieldy with 600,000, that's true. You would have about 1,000 dimensions that describe every word and how much of something is in those words. But for purposes of principles from practice again, let's go back to our simple universe where there are only 3 dimensions. So now we have these words that are described in how much they have of these 3 dimensions. Now we can do something really cool. We can actually do mathematics with language because they're represented as numbers. Let me show you. Now, we have our universe with the 3 dimensions. We take a word, we take the vector for that word. So we take king, which was almost 100% royalty, almost 100% masculinity, and almost 0% femininity. And then we simply, literally subtract a man. So we take a king and we subtract a man. Let's do the math here. What happens to the royalty? So we had 99% royalty on the king minus 0.01% royalty on the man. That means 0.98% royalty. We had 99% masculinity in the king minus 99% masculinity in the man. So now we have 0% masculinity. And we had 0.05% femininity minus 0.05% femininity. So we have 0% femininity. So we took a king, we subtracted the man from the king, and we got a new word vector. What word do you think this is? What is it that is 100% royalty, but is genderless? It is royaltiness, pure royaltiness. Okay, so now we got a new word. What happens if we take pure royaltiness and we add a woman? So let's do the math. We have 98% royaltiness plus another 2% royaltiness in the woman. That means we literally get to 100% royaltiness. We had 0% masculinity plus 0.01% masculinity, so almost 0% masculinity. We had 0% femininity plus 99.9% femininity, so almost 100% femininity. So now we have this new word vector, which is almost 100% royalty and almost 100% femininity. What is that? Well, it's a queen. So now all of a sudden, you can take a king, you can subtract a man, you can add a woman, and then you have a queen. So now you're quite literally doing math with words. And this is why vectors are so interesting and useful, because they encode how much they are of something. So this can be really useful, and I'm going to show you how. But first, a question might be, how would you go about doing this in practice? In theory, again, you as a human, you could just sit and guess at these percentages. Actually, we just did. So intuitively, if you can do it, the computer could probably do this. But how would you do it statistically? Well, again, there is the internet. So here's one way of doing it. Let's say that you take the entire internet, or maybe Wikipedia, and for any word you want to learn, in this case, for example, the focus word is learning, you just say how close the other words are to it in a sentence. So for example, in this sentence, an efficient method for learning high-quality distributed vector. You can see that the word for and high are right around the word learning. So that means the computer will give it a high score because it's literally close to the word learning, whereas the word inefficient and distributed vector are further away, so they will get a lower score. So if you just take that simple method of you go through sort of all the documents on the internet and you say, for this word, what are the words that come up really, really close to this word on the internet? They are probably related to this word, so they will get a high percentage. Words that are far away from this word in all the documents on the internet, they get a low percentage. So now, just like with the LLMs, you have a scalable statistical method of learning these statistics and learning these vectors. So now, hopefully, you have an intuition for not just what a word vector is, but also how you could automatically learn word vectors for sort of every word on the internet, just based on how close it is to the other words on the internet in sentences. Okay, so now you kind of know what a vector is, but why is it useful? Well, it turns out that if you go through, for example, all of Wikipedia, and you do this, it's going to turn out that if you think of this in our simple three-dimensional universe, where there are only 3 dimensions, there's royaltiness, masculinity, and femininity. And you have this vector king, for example, that is almost 1 on royalty, almost 1 on masculinity, and almost 0 on femininity. You can think of that literally as a vector in this simple three-dimensional space that points in a certain direction. Or another way to think about it is that it is in a certain place in that space. So it's going to turn out that words that are similar, if you think about it, that have a lot of the same dimensions, they're actually going to sort of be pointing in the same direction or be close to each other in this vector space, right? So the word king and queen, we just said they're going to be close to each other because they're both going to be high on that royalty value. They're both going to have a bunch of other words that they have in common or dimensions. And if you can intuit that words can be close to each other or far away from each other in this vector space, then it's pretty intuitive that sentences that are just combinations of words, if you literally take the vector for every word in a sentence and you sum up how much royaltiness and how much masculinity and femininity are in all of these words, you're going to get a sum value for the entire sentence. So now you can also say how close sentences are to each other in this very simplified three-dimensional world. So it turns out that if you look at something like lion is the king of the jungle, that sentence is going to be pretty close in this vector space to the tiger hunts in this forest. And that kind of makes sense to you as a human, I think, because lion and tiger, they're somehow similar. They're both animals, so they will be high on the animal dimension. They're both sort of majestic. Maybe they're high on that majestic royaltiness dimension. Jungle and forest, they should be close, right? The trees in there, they're similar. So it kind of makes sense to you as a human that lion is the king of the jungle is probably close to tiger hunts in this forest. And if you look at the vector dimensions, it will be, because it will score high on the percentages on the same dimensions. Whereas a sentence like everybody loves New York, it's probably going to be further away in this vector space from these sentences. So again, now you have this way of taking a language and not just turning it into a single number, but turn it into several numbers that allows us to understand that certain words or sentences are more or less similar to each other, or what is called close to each other. We thought about it in a simple three-dimensional world, but the real world then would be, if you take every word in the dictionary, 600,000 dimensions, but it doesn't matter. Think of it as 3 dimensions. It's the same concept. Okay, why is it helpful to understand if things are close to each other or far from each other? Let me give you an example that I think will drive this home. Here's another world. This world has 3 other dimensions. It has how much something is rock, how much something is classical, and how much something is EDM, electronic dance music. Again, simple world. There's only rock, classical, or EDM as dimensions in this world. And now we take something that isn't a word, but it's actually a song. Here Comes the Sun by the Beatles, Für Elise by Beethoven, Levels by Avicii, and Bohemian Rhapsody by Queen. And now we try to give percentages for how much rock, classical, and EDM there is in each of these songs. Let's see if we can agree. So let's start with Here Comes the Sun by the Beatles. It is pretty much a definition of rock, so maybe it's 98% rock. There's not a lot of classical in there. Let's put it close to 0.02. And there's very little EDM. It wasn't even invented then, so 0.01. So now we have a vector for Here Comes the Sun by the Beatles. What about Für Elise? Well, not a lot of rock in there, so about 0%, 0.01. A lot of classical, sort of the definition of classical, so 99%, and almost no EDM, 0.05. Then Avicii comes along, and there isn't that much rock maybe in Levels, let's say 0.02. Not a lot of classical, 0.01, but a lot of EDM, obviously, kind of defined EDM. So let's say 0.999, or 99.9%. And then Bohemian Rhapsody is interesting because it's not just one of the things. I think most of you would agree that Bohemian Rhapsody is a pretty unique song. It has a lot of rock in it, so probably 99% rock, but actually has a lot of classical in it as well, maybe 99% classical. But it doesn't have a lot of EDM, so maybe 0.05. So now you've taken songs, and if you imagine that you as a human, you would sit and take all the songs on Spotify, and you would score them on these dimensions. Now it's really useful to understand which of these songs or words, if you think of the song, each song as a word, are close to each other in vector space. So you can say that this user listens to Fy Release. So they may be interested in Bohemian Rhapsody, and they will be close to each other in vector space because they both score high on classical. But they may not be interested in levels because it doesn't overlap at all on any of these dimensions. So levels and Fy Release will be far away from each other in vector space, as will Here Comes the Sun. All those three will be far away from each other. But Bohemian Rhapsody will be quite close to both Fy Release and to Here Comes the Sun because it's high on rock. So this is actually how recommendation systems work, like Spotify. But one question then is, I explained to you how you could learn these vectors for words. You could go through the internet, you could take the text on Wikipedia, and you can say, this word is close to these other words in all the documents on the internet. How would you go about doing this for songs? You almost wish that there would be a lot of documents where songs are close to each other. That's what a playlist is. So Spotify has a few billion of these playlists. And if you think of this playlist as a sentence, you can literally take the song in the middle and say, how close is this song to all the other songs in this playlist? Or if you think about all the playlists as one big document, if they're in the same playlist, they are probably close to each other. So songs are in the same playlist, they would score high relative to each other. So you can see how you could build a vector where you kind of understand how much of every song on Spotify is in every other song on Spotify as a percentage. And now you have a vector representation of every song on Spotify. And because it's a vector and it lives in this multidimensional world, you can do recommendations. So a taste profile on Spotify is actually, if you simplify it a little bit, just all the songs that you listen to and all those dimensions added together. So you get a score for how much classical is there in all the songs you listen to. You sum that up, you divide it by the number of songs, and then you have a classical score for that user. You do the same for rock, the same for EDM, the same for jazz, and now you have a taste profile for that user. And now you understand where that user is in the vector space. And you can say that these two users, they have almost the same vectors, they're close to each other, they have the same music taste. So now, not only do you understand what vectors is and vector space, embeddings, codes, distributed representations, it's all the same thing. It's all what I just showed. There's different names to make it seem harder than it is. But you also understand why it's useful. And you actually happen to accidentally understand how a recommendation system works. All right. So now, you hopefully understand what a large language model is, how Chat GPT works, what a word vector is, and why it's useful. But I also promised to explain to you how it is that you can make images from text or images from noise and even music from noise. So in order to do that, we need to go one step deeper. I'm going to explain in a simplified way what a neural network actually is. And again, in practice, very complicated. In theory, not that complicated. So the neural network is loosely based on the biological neuron that we have in our brain. And it looks something like this in a cartoon. So you have these little arms on the yellow part called dendrites. Those are the inputs. Let's say that they get electrical signals from your retina. So lights hit your eyes, they're electrical signals. They go into these dendrites in the yellow part. These things combine. So let's say that this particular neuron, it is looking for vertical lines, that's a vertical line, or horizontal lines in front of your eyes, right? And so maybe this particular neuron, when it gets a pattern of these electrical signals, these dendrites, they get a value, it's going to hit some threshold that says like, hey, I think I'm seeing a vertical line here. And then it's going to send a spike along this axon to the right. That goes to the next layer of neurons, that goes to the next layer of neurons. This is all that a neuron does. It takes a few input signals, it combines them, and if it hits a certain threshold value, it's going to say, hey, I'm seeing something here, and it's going to send a signal or a spike. So what computer scientists did was they did a very simplified, idealized mathematical version of the biological neuron called the artificial neuron. So the arrows pointing in here are the equivalent of the dendrites. So you have A1, A2, A3. These would be the electrical signals from the eyes. In a computer world, they would be the pixel values from a camera. They come in, they get multiplied by these things called W1, 2, 3, which are weights. I'll talk about that later. And then as you take the electrical signal, you multiply them by the weights. If this cell body, the circle in the middle, hits a certain threshold, for example, the cell says, I think I see a vertical line, it is going to send a spike or a signal to the right called Z. So it's a very simplified version of what the biological neuron does. Okay, if you didn't fully get that, don't worry. You'll see it in practice now. Let's say that we have a picture of a cat. Why not? The internet is full of cats. Now, let's say that you take a camera and you take a photo or a video camera and you point it towards this cat. What the computer is going to see are pixel values. Remember, to a computer, everything is numbers. The pixel values are just numbers. Maybe we simplify it and say it's a grayscale. So number 0 is black and the number 255 is white. And in between, there's shades of gray. So just numbers. So now you put up a bunch of these artificial cells. And each of these inputs gets a pixel value. And now you can imagine that maybe the top neuron there, it is going to spike if it sees maybe a diagonal line like this, right? And it says like, hey, I see a diagonal line. And then the neuron below it, maybe it's looking for a diagonal line in the other direction like this. And it's only going to spike and send a value to the rest of the network if it sees that. And now you add a second layer of network. This is why they're called deep neural networks. You add more and more layers. And so now the second layer of neurons, it can get a spike from the first layer and says, the first layer saw a diagonal line like this and a diagonal line like this. And the second layer neuron is going to spike only when it sees both of those in the first layer. So maybe this is actually the shape of the tip of a cat's ear. And maybe this line is the shape of a whisker. And so you go one more layer and it combines all of these signals. And at the very end of this layer, which can be very deep, the last neuron would actually say, I see all the inputs from all of these layers of what is actually a cat. And now you have what is called a cat classifier. So how does this work? Well, if you look at this, you can almost intuit that if you have all of these weights, the W1s and 2s and 3s, if you had infinite time, you could imagine sitting and tweaking all of those numbers so that these neurons happen to hit that threshold and spike exactly for the shape of a cat from many, many different directions, right? So some of these neurons are looking for tips of ears, some are looking for neurons, some are looking for eyes and paws and so forth. You could imagine that if you had infinite time, you could tweak all of these parameters in the network so that it only spikes all the way back to the end when there is a cat, but not when there is a car or an airplane or anything else. So again, in principle, not that hard to intuit. In practice, pretty complicated. How would you tweak these parameters? Because there can literally be many billions, almost up towards 1 trillion now of parameters in a network like this. But we're on the theory level where things are simple. So again, there's one thing you should understand here. Scientists actually a long time ago came up with something called backpropagation. And what that means is they found a way for the model to teach itself all the right parameters. And the way to think about this is you have a lot of pictures of cats and things that are not cats. And instead of a human sitting and tweaking these parameters themselves, what you do is you just initialize all these parameters as random numbers. It's completely random. So if you think about it, the first time you show this network a cat image, it's going to guess completely wrong. By definition, random, right? But it also means that by random chance, sometimes when you show it a cat, it will actually guess that it was a cat. And then what you do is through something called backpropagation, you say like, hey, wait a minute, you happen to guess correctly. Keep those values. In fact, move all the W values a little bit in that direction because you were right. And then when it guesses wrong, you do the opposite. You move them in the other direction. And then you do this for literally tens of thousands, hundreds of thousands, millions of images, where you say like, is this a cat? And it says yes. And then you say, good network. Move a little bit, move all these values a little bit more in that direction. Then you show it maybe an airplane, and it says it's a cat. And then you say, bad network. Move all the values a little bit in the other direction. And you just keep reinforcing it. And if you do this millions of times, eventually all of these parameters, because you reinforce the good behavior, are going to end up on finding exactly the combination of shapes in this image through multiple layers that represents a cat, but not a dog and not anything else. So this is what a neural network does. Again, it's quite simple in theory, even though it was hard and took a long time to do in practice. So this is important to understand, because when you understand this notion of taking numbers, multiplying them, seeing if they go over a threshold, then taking those numbers, multiplying them, now you can understand how these image generation networks and so forth actually work. So here's another concept that I think is very interesting to understand. Intelligence is compression. Now, this is stated as a fact. It's not a proven fact, but it is a theory that a lot of people have, that one way to think about intelligence is as compression. What do I mean with that? Well, back to intuition. If you speak to someone who knows something very well, they're usually very good at explaining it, right? Whereas if you speak to someone who doesn't know something very well, it's hard for them to explain it. So the person that knows something well can explain something in a simple way. That usually means that if they can explain it in a simple way, they understand it better than if they can't. So already there, you can see that there's something around compression, right? Probably that person spent a lot of time on this problem, and they learned to take all the details and compress it into what it actually means and understand it deeply. And then all of a sudden, they're able to explain it. So there is actually even this thing on the internet called the Hutter Prize, which is a competition where you're supposed to take all of Wikipedia and try to compress it as much as possible, including its own extractor actually, without losing the information in Wikipedia. Because the idea is that in order to compress Wikipedia effectively, the system that compresses it is going to have to understand a lot about the world. Like, you have to be smart in order to compress. You have to understand the dimensions of the world really well to be able to compress the world. And like I said, this is intuitive. Humans that can explain things simply, they usually understand more. So the system that compresses it had to develop understanding. So think of intelligence as a side effect, a necessary evil of being able to compress information. So in this Hutter Prize, you can actually make money for every percentage that you can compress Wikipedia. In that case, losslessly, without losing any information. But in general, the concept is if you can compress something and retain most of the value, you probably understood it really well, because you could represent the same thing with less information. And representing something with less information kind of requires understanding on the part of the system that compresses it. All right, let's get a little bit more practical here. So remember, to a neural network, everything is just numbers. Language is numbers, pixels are numbers, samples are numbers, DNA sequences are numbers, anything is a number. So if we take this neural network that looks a bit funky, let's say that we take a sentence like a cat jumping out of a window, which then again will be represented as a sequence of numbers. So 1, 2, 3, 4, 5, 6 numbers. And then what we do is this neural network is just take those 6 numbers, and through these neurons, it multiplies it and adds it, and has it represented by fewer numbers, then multiplies and adds it again. And in the middle, it only gets 3 numbers to represent those 6 numbers. I know it seems weird, but hang on. So we force the network to take 6 numbers that represent the full sentence and represent it with only 3 numbers. And now you ask the network to do the opposite. From these 3 numbers, again, it multiplies it and tries to turn it back into 5, 6, or 7 numbers. In this case, 1, 2, 3, 4, 5 numbers. So all we did was we told this network that here's a sequence of numbers that to us means a cat jumping out of a window. You have to compress those 6 numbers to 3 numbers and then expand without any new information, just from those 3 numbers, back into the same sentence, or as close as possible that you can get. So the entire training task here is to take a sentence, compress it, and try to recreate the same sentence. So in a perfect world, the output would be a cat jumping out of a window, the exact same as the input. So you train this network again and again to try to compress these numbers and recreate the same numbers. And it's not going to be possible for the network to recreate the same numbers perfectly, because when you go from 6 to 3 numbers, you will lose information. So by definition, you lost information. You lost at least those 3 numbers from 6 to 3. So it's going to do the best it can. And that means that it's going to have to pick these 3 numbers in the middle, back to dimensions. It's going to have to pick the 3 dimensions, the 3 numbers, that sort of best describes the world. What do I mean with that? Well, it means that if you look at something like a cat jumping out of a window, maybe these 3 numbers in the middle, they represent something like not quite a cat, that's too detailed, but maybe a pet. And maybe the second number represents something like going in and out of something. And the third number represents something like an entity or a house. So what you will get on the output is something that is similar conceptually to the sentence you put in, but not quite the same because information was lost. So if you put in a cat jumping out of a window, maybe what you get out is a pet leaving the house or a dog leaving the house, right? Because the system had to pick, it had to lose information, it had to abstract, it had to pick the most important dimensions to do as well as it could. It had to compress. So what this means is that this thing in the middle, the embedding code, again, the vector, hopefully, if you do this right over a lot of sentences, is going to find the numbers that are the best representation of the world that is being trained on, which in this case would be the text of the internet, right? It's a textual world for this network. This is called embedding. So you take the sentence and you embed it from 6 numbers into 3. And the network, if you train it correctly, is going to choose the right dimensions that give the most information about the world, that completes the training task the best. So again, it seems like a pretty useless task, especially for language. Why would you want to get like a different version of the same sentence out? But maybe an example that would be easier to understand right now. This is important to understand for the diffusion models. That's why we're going through it. So if you instead think about images or maybe video, you could imagine on the left side here that you have an image or a video that takes a lot of space. And when it comes to images, you know that you can compress it and actually lose a lot of information, and it's still good enough, right? This is what all image formats do. They compress the image so that you can send it over the internet using much less data than the actual original image. So one way to create that compression would be that you take an image, for example, of a cat on the left, you force the network to take all those numbers, all those pixel numbers, and represent them there in the middle with much fewer numbers, and then just try to recreate the same image of the same cat as well as it can. And if you do this right, it's going to be very good at recreating almost the right image. And if you teach the network to do it as well as possible, it's going to find the dimensions that are most important to keep there in the middle in order for a human to think that this is still the same image of a cat. So the network is going to learn itself to compress to the most important dimensions. For example, humans tend to care a lot about low frequency things in images and not as much about high frequencies. So we'll probably learn to keep some of the low frequencies and not the high frequencies, etc. But it's not important with the details. The whole concept is it takes a bunch of numbers, in that case of the image, pixel numbers. You force the network to try to pick the best representation with much fewer numbers that still keeps as much as possible about the information in that original image, and then recreate it. So if you do that, now you actually have a compression algorithm where you can take an image, but instead of sending the image over the internet, you just embed it and you just send this code in the middle. And the receiver has the other side of this network and then decodes it back into the full image. So now you saved a lot of bandwidth. This is called an autoencoder. And it is actually how some compression algorithms are done on the internet. So now you not only understand what a vector is, what a word vector is, but you also understand how you would actually create this vector and what an embedding is, which is a network that through training takes a piece of text, an image or something, and automatically creates this vector for you. And it automatically, importantly, chooses the best dimensions. Instead of having 600,000 dimensions of the world, you force it to choose much fewer. And in forcing it to choose fewer, you force the network to actually become intelligent, at least according to some definitions of intelligent, in how it picks those dimensions. All right, we're almost there. So what about images, music generation, video, etc.? There's only one last thing you need to understand now, that you understand all of this, in order to understand how something like Stable Diffusion works or Midjourney or something like this. And that is this notion of diffusion models. So diffusion models is actually also something that I think conceptually is very intuitive. So remember this neural network, right? Let's say that you take an image, the one to the left here called T0. And what you do is you just add a little bit of noise. So you go from the image on the left to the second image on the left. You add a little bit of noise on top of this image. And now you train a neural network to simply try to find that noise and remove it again. And if you look at those images, the difference between the first and the second image is very small. It is intuitive, I think, to you that you could remove that noise if you just had time. And so why couldn't a neural network? It doesn't seem that hard because you just add a little bit. So that's the first step. So think of it almost as you have a separate neural network that just removes a little bit of noise from the second back to the first image. Now you take the second image with a little bit of noise and you add a little bit more noise. And now you train a network to just remove that additional noise. Like the image that you added the noise that you added to the third image back to the second, not all the way back to the first. It's just one step at a time. So every step here is just removing a little bit of noise. And now you take that third image, you add a little bit more noise, you train a network to remove just that noise. And you keep going. You take that image, you add more noise, you train a network to remove that additional noise, etc. And when I say remove, you train a network to identify this was the noise added and simply deduct it from the picture, sort of recreate the original image. So hopefully it's intuitive that you could do this. So you have like a network that can take an image at any stage and remove that additional little noise. Because if you think about it, at every stage, it was a deceptively simple little task. But at the end, you've added so much noise that there is pure noise in the image. There is no image anymore. So to the right, the task is actually to remove the last piece of added noise from complete noise to almost complete noise in the second to last image. All right, so again, this seems like a stupid task. Why would you take a perfectly good image and destroy it slowly and train a network to remove a little bit of noise at a time? Well, the really cool thing is now you have this network that starts with a good image, learns to remove a little bit, makes the image worse, removes a little bit again. But if you now take this network and you kind of run it backwards, so instead of taking the neural network that is furthest to the left, that removes just a little bit of noise from the good image, you start with the one to the right that removes a little bit of noise from the pure noise image. What you can do is this. You start with just random noise, and then you run the network backwards. And what will happen is essentially, what you've done is you've trained a network that is desperately trying to look for sort of face-like noise in an image. And so it takes this complete noisy image, and even though there's nothing there, it's going to say like, hey, I've been trained to find sort of a face-looking noise in here, or if you want to simplify, I've been trained to find the rough outlines of a face in here. I think I see something there. And it's going to remove a bit of noise that actually makes it look a little bit more like a face. And then in the next stage, the next sort of network, even though it's the same network, but think of it as separate, takes that image and says, I've also been trained to remove noise, to find like face-like noise here and remove it. I think I see the outlines of the face in there, even though there's hardly anything there. In the first stage, there was nothing there. It was just noise. In the second stage, there is actually a little bit of a face there because the network itself removed exactly the pixel that made it look more like a face. And now the next step says, hey, wait a minute, I see the outlines of a face. I'm going to remove, I've seen this before. I'm going to remove this noise, which is going to make it look even more like a face. Third image takes over, says, oh, I clearly see the outlines of a face here. I know exactly what kind of noise I should remove to make this look even more like a face. And you just keep going. And at the end, all the way to the right, you will have created a face out of pure noise, meaning a face that actually never existed. So to be clear, not a copy of a face that existed. You train this diffusion model to remove noise across, millions of different faces. So it didn't learn to create a specific face, it learned to create general faces, and is looking for general face-like noise in this first random noise image. And so this is how you get to something like this. This is a site called thispersondoesnotexist.com. That every time you go in there, it literally generates very believable faces of people that never existed. Now, for those of you who know more about this particular site actually doesn't use a diffusion model. It uses something called a GAN that came before Generative Adversarial Network. But the idea is the same. Diffusion models have sort of taken over from GANs. So now we know how we can generate at least faces out of pure white noise, like one particular thing. But I promise to explain to you not just how you can create one thing, but how you can do something like what Stable Diffusion or Midjourney does. And on these services, you can do more than just get many versions of the same thing, like a face or something like that. You can put in text, and you can ask it to generate, for example, a picture of an astronaut riding a horse on the moon, which is something that you can Google, for example. And so how does that work? How does this text conditioning work? Well, it is a diffusion model. So it does what I just showed you, but it does something more. This is why you just learned about vectors. So let's go back to this thing of intelligence is compression and how you actually condition on text. So I showed you this network that we said looked pretty useless, where you take a sentence, you sort of compress the numbers in that sentence to fewer numbers that hopefully somehow captures the important dimensions of the sentence, and then you try to expand it to the same sentence again. And we said it was pretty useless, but now it's going to turn out to be pretty useful. So what you can do once you train this network is you cut off the right part and you just keep this part. So now you have a machine that you can give a sentence in English and you can ask it to embed it, to compress it to these numbers that represent what is in that sentence as well as possible. Okay, so now let's imagine that you're a service, let's say a social network or search engine that has a lot of examples of images and captions to that image. So for example, maybe a picture of a cat staring at you and the caption, a cat staring at me. Now what you can do is the following. You can take that caption, a cat staring at me, and you can take this encoder. You can take that sentence, which then again is just a sequence of numbers, so 1, 2, 3, 4, 5 numbers. And you can ask this network to compress it into these 3 numbers that hopefully captures what it means to be a cat staring at me. And now we take the diffusion model. So we take the image that belongs to this caption. As before, we add a bit of noise, then we add a bit of more noise, then we add a bit more noise until it's complete noise. And we put in this neural network in between that is going to try to remove the noise. Now this is exactly what we did with the faces, right? So if we just did this, we're going to build a diffusion model that always finds cats staring at you, which is not what we wanted. We wanted something that is steerable. So we're going to do one more step. We're going to take this other network we had that takes the sentence, a cat staring at me, embeds it from these 5 numbers into these 3 numbers, the code, the pink thing. And as this diffusion model is trying to remove the noise between the second and the first picture, we're going to give it these 3 numbers as a clue, right? So remember, we're giving it the picture of a cat staring at you, and we're giving it the 3 numbers that represent a cat staring at you. So you can think of the diffusion model now as having a clue about what kind of noise it's looking for. It's not just looking for one type of noise. It's going to say like, hey, these 3 pink numbers, I've seen them before. It means there's probably a cat in here, or there's probably cat-like noise here. And then you do that, and at the next step, you give it the same clue, like you're still looking for cat-like noise. The next step, you give it the same clue. Remember, to a neural network, everything is numbers. The pixels are numbers, but these sentences are also numbers. It doesn't really understand that one is images and the other is text. It's just saying like, I've seen these numbers. When I saw these numbers with these three numbers on top, there was always cat-like numbers in there, or cat noise-like numbers in there. So let me try to see if I can find a cat in here, staring at me. So you do this, for example, for this image, a cat staring at you, and then you have other similar images, but with different captions. So instead of a cat staring at you, maybe another image is a cat jumping out of a window. And now this encoder at the top is going to embed that sentence, which is 1, 2, 3, 4, 5, 6 words, 6 numbers, into 3 numbers. These 3 numbers would probably be similar. There's cats in there, right? But there's also the concept of jumping, and there's not the concept of staring. There's a concept of window and so forth. So this vector will be similar in the dimensions, but a little bit different. And now you do the diffusion on that image. So again, the network has this clue, these 3 numbers, as it's trying to remove the noise, so that it can understand what kind of noise it's looking for. So remember, in the first process, we always removed the same kind of noise, face-like noise. But now we're doing a diffusion model that gets a clue for what kind of noise it's looking for. And so we're very focused on cats here, but this could be anything. It could be a picture of an aeroplane and the text saying an aeroplane flying. And then it's going to kind of learn what aeroplane-like noise looks like, or the removal of aeroplane-like noise. And what you can do is you can actually take something like a song, right? A song is an audio wave, but it turns out you can take a piece of audio and you can transform it into what is called a spectrogram. So a spectrogram is the visual representation of a song. It kind of says how much of every frequency is in a song at a certain time and the magnitude of that. It doesn't really matter. If you just imagine that you can take a piece of audio and transform it into a spectrogram, you can represent audio as an image. So now what you can do is you can take a song, for example, Obladi Oblada by the Beatles. You can take the spectrogram of that song, and you can take the description in text, literally, Obladi Oblada by the Beatles, or maybe a song, the song Obladi Oblada by the Beatles. You embed that, so now the code is going to somehow represent the concept of a song, the concept of the Beatles, and some other things that we don't fully know. It's going to find the best representation of this sentence. And so now you're giving that sentence, the song Obladi Oblada by the Beatles, as the clue to this diffusion network as it is trying to find this spectrogram. And so you're going to teach it to first of all find spectrograms, but you're also going to teach it, if you show it many spectrograms with many different types of music, a certain type of spectrogram. So what happens now is once you train this network on millions of different types of images, as I said, cats, dogs, airplanes, images of music, whatever you want, you can now take this network, you can turn it around, and you can start with just pure white noise. So there is no structure in here. There's literally nothing in this picture. And now you take a sentence that never existed. Let's say an Avicii song in the style of the Beatles. And as you've trained this network, this encoding process, hopefully, will have captured the dimensions of the world. So we'll know what what Avicii is and what it means. It'll kind of know what a song is, that it should do a spectrogram now and not a picture of a cat, and sort of what the Beatles represents and what those kinds of spectrograms look like. And so it's going to embed this into this code that in our simplified example is just 3 numbers. It's not 3 numbers in reality, it's more numbers, but for purposes of simplicity. And now we take this pure white noise, we give this code as a clue to the diffusion model for what kind of noise it's looking for. And the interesting thing again here is now we're telling it to look for a kind of noise that actually never existed before, Avicii song in the style of Beatles kind of noise. And it's going to try its darndest to try to find that kind of structure in this pure white noise. So it's going to remove noise that makes it look a little bit more like a spectrogram or a song of Avicii in the style of the Beatles. And at the next step, we give it the same clue and say, try harder. try to really look for the structure of an Avicii song in Stable Beatles. Remove some more noise. And we do it again, and we do it again. And if you're interested, in reality, these diffusion models have about 50 of these steps. And at the end of the line, at the 50th step, you're going to get a spectrogram of a song that never existed, that hopefully is an Avicii song in the style of the Beatles, when you transform it back from a spectrogram into pure audio. So now you're finally there. Hopefully, you'll be the judge. Tell me what you think. You have some intuitions about how it is actually possible to create new novels, poems, images, even music out of just text or even white noise. And hopefully, you feel like we managed to debunk this conspiracy a little bit. Thank you very much for paying attention.